So this week is dangerously interesting. Uh, so final signups are open. You don't need to race to do it, just you need to get signed up. But we're counting down to 1 week to applications, 1 week to invention. We're up to the weekly assignment deadline, and then you present. So it's all about triage. And the danger is I'm going to excite you with a bunch of new things this week. So you'll need to manage your time and attention for how you use this relative to finishing your project. So the idea of Wildcard Week is every year we review the cycle, and there's always questions, what about, and then fill in the blank with some other technique we could cover. And so there's a suggestion to add a new skill, and then we go back to the schedule and say, what old skill do you want to take it away? And it obviously sort of all the other things we've covered are so important, we can't easily subtract any one of them. And so the idea of Wildcard Week is instead of everybody doing the same skill, everybody can do a different skill. This week, you pick what you're going to do. The rules are you're going to design and produce something. It's a digital process. And what that means is it's not simply manual skill. There's a computer design and manufacturing involved such that you can document how to do it so somebody else can reproduce it. And then one of the rules for this week is you have to document. In the past, I've told you the assignment. This week, you tell us the assignment. You have to tell us what your assignment is. And the big one is this. It has to be something not covered in another assignment. So it's not as simple as using a different 3D printer. I'm going to give you lots of examples. It has to be a skill we haven't covered. And in part, the opportunity is to take advantage of special capabilities in the lab you're in. And in part, the goal is to bring in new capabilities. This is like a training farm team to test new skills that might be of interest across all the labs. So the class is going to be split in half. I'm going to give you a tour of options. And then before Wildcard Week, this was actually Composites Week. And so the second half is I'm going to cover composites. And the example I showed to Barcelona was this gorgeous kayak as a large format machining plus composite assignment as inspiration for that. So here's the tour. What I'm going to go through is not exhaustive. It's not a limit. It's just to give you a feeling of options. So one is multi-axis machining. This is a big mill in my shop where it moves X, Y, Z, plus the bed rotates and the head swivels. Because we didn't make everybody do 3-axis machining for molding and casting, it would be fine this week. Even in the past, for make something big, that was 2.5D. You moved in a plane and then stepped down. Full 3-axis machining, where you move all 3 axes, is fine for this week. And then if you have access to 4 or 5 axes, even more so. So one option is use this week to learn about full 3-axis machining. If you have it, this is an electric discharge machine that uses a plasma around a wire for metal cutting. This is a big water jet cutter, but increasingly there's small tabletop water jet cutters that cut with a supersonic jet of water with an abrasive garnet that machines glass, stone, any material. Plasma cutters are another option for metal cutting, where it's a torch that generates a plasma. These make a lot of sparks and flames, so you need to use it similar to where you would use a foundry, but as an option for metal cutting. Then this is a much higher power laser. Instead of 100 watts, this is a 1,000-watt fiber laser with enough power to do metal cutting with a laser. And then at the opposite extreme, this is a micro machining laser, a very high resolution laser that can make parts on the scale of microns. So any of these, oh, sorry, I missed one of our favorite ones. This is a giant flatbed cutter. This is like a vinyl cutter, but a 4 by 8 foot bed for large format cutting. So any of these would be options for machining. And again, the multi-axis you can do on a tabletop mill, but using all 3 axes to do rough and finish cutting, to do full 3-axis machining. So that's one option. If your lab is set up for welding, just welding alone, it doesn't count. But if you connect welding with these other tools, so you use a computer to design the parts, and then cut them out and MIG or TIG or spot weld them. But using welding to join parts you fabricated with the other tools is fine. Then for molding and casting, this was a fun project to do vacuum forming, where Brent actually made the vacuum former. So I had mentioned the killer app for vacuum forming is packaging. And so you heat a plastic, soften it, and pull a vacuum. And there are now roughly $1,000 tabletop vacuum formers that are quite capable. So that would be fine. And then we saw in this cycle, one of the machine building projects was rotocasting. So rotocasting is where you tumble the mold and it coats the interior surface to make a shell rather than a volume. So those would be new kinds of molding and casting. Then something that is sufficiently different is using the laser or the vinyl cutter, but for folding. So Eric Demain is a colleague who turned origami into a rigorous mathematical subject. And one of the things he's known for is curved creased origami, where he worked out the algorithms to fold these kinds of structures. So that's Eric. This was actually Sam, who made the kayak. This was his thesis with me. And he did a lot in this thesis. He showed, given a 3D form, how you make a 2D cut pattern to fill the 3D form. He designed machines to do the folding. And then he designed ways to tune the stiffness to range the elasticity. And then he designed materials that either maximize energy absorption or maximize energy return. And then this is an article on one of my students currently who's doing kirigami, and it happens he's doing it in metal, where once again he designs folds to fill 3D forms. Origami is folding with score lines. Kirigami is having cut lines as well as scoring lines and folding. So for these ones, these use tools you've already used, the vinyl cutter or the laser cutter, but it's a completely different operation to do with it to fold. Okay. Next is robotics. So these are universal arms. Elephant Robotics has, let's see, there's some more links about, folding. Elephant Robotics has cheap and cheerful, low-cost arms that are very general programming platforms. So a fine thing for this week is programming robotic arms to do anything you want to do with them. It can be an assembly task, it can be processing, manipulating. For inspiration, these are colleagues in Zurich who program big mobile robots to do construction, to build by placing parts. They've got an amazing warehouse. This is a picture of it, full of these big robots as a test bed to make giant structures. So you can do robotic construction. And then there's a whole range of soft robotics. So this was Adriana, one of the gurus, and with molding and casting, what you can then do is make molds that you inflate with air pressure, and you can make grippers and manipulators and dexterous objects by, again, the skill here is molding and casting, but then by inflating it, it turns into very interesting actuation. This is a colleague at Harvard who helped launch that field, and this is a good review of it, to make all sorts of deformable soft robots. This was a former Fab class, MIT how to make student who developed this platform. For pneumatics, you need the pneumatic generator. You might want multiple channels. You need an easy programming interface to it. And so we developed this really nice open generator for portable personal pneumatics. He's done a really good job on creating and documenting platforms that let you make all these kinds of things. So that's Flow.io. And then finally, a great thing for this week is inflatables. I showed this earlier, but I never get tired of showing it. This, again, is a company that includes, at the time, oh, actually, this is funny. In a minute, you're going to see Sam. So that's Sam. Oh, no, actually, that's not Sam. That's another. But what's going on here is there's 3 bladders. They're sewn. And then by selectively inflating the bladders, you make rather than a rigid robot, a dexterous, soft robot. So that's robotics options. Then this is a pick and place, and these have come down way in cost. Here, I'll make a note to link the Lumen. Let me get to the right place in my notes. So the last pick and place I showed you was a $30,000 one. This is a $2,000 open source one. And lately, my lab has been making more use of this kind because they're the barrier. They're easier to use. They have an open source software lineage. It's easier to get started with them. So using a pick and place to produce your electronics would be fine for this week. And then I've linked here in programmable logic is PLDs and FPGAs. And so, yeah, Sahin has linked a FPGA wildcard example. So a field programmable gate array is a sea of logic with switches you electrically switch that essentially, not essentially, they let you make reconfigurable versions of integrated circuits. These are often used before you make a large integrated circuit. You test it in a FPGA. So learning to use FPGAs to make custom circuits is something you can do this week. Originally, they were all proprietary. This is a nice project, open sourcing a tool chain for FPGAs. Okay, then for embedded programming, yeah, Dylan has included a famous Monty Python scene. We've covered embedded programming. I talked only briefly about TensorFlow Lite, TinyML, ESPDL, Edge Impulse. These are all platforms for embedded AI. You can't run large language models on a tiny 412, but you can use these to recognize motion, sound, patterns, things like that. So generating embedded AI code is a fine thing for this week. And likewise, I covered getting data in from a camera, but I didn't talk about doing things like recognizing faces or tracking people in a scene or tracking objects moving. And so using one of the proliferating AI cameras, using OpenCV, uh, um, so to do machine learning or machine vision, it builds on the skill of embedded programming, but now instead of just you writing the code, it's using machine learning, and that counts as a new skill for this week. For food, yeah, just memes aren't enough for Wildcard Week, Dylan. This is an article on a colleague, Ahad Lipson, who's been a pioneer in many kinds of digital fabrication and now is doing food printing. And uh, let's see, I don't know if this one is still active. I'm not sure if he's still doing this. Okay, yeah, I thought that that site had expired, unfortunately. Um, but food production processing, so extruding, molding, shaping, manipulating food. Um, uh, let's see, updating my notes. Uh, Digital gastronomy, um, uh, manipulating food, again, is different enough that would count for this week. A really good one is materials. So I've highlighted Materiome, this great project on creating open source libraries of material production. And so this is aiming for starting for what's available of coffee grounds, eggshells, seaweed, where, depending on where you are, easily available materials, and then recipes to turn them into soft or transparent or rigid materials. So producing your own materials and then using them in an existing machine, like milling or laser cutting, would be a nice thing to do this week. Likewise, this was a early version of making an open materials tester to do materials characterization. And then this was a version of making a 3D printer that can do materials measurement. It does what's called rheology to learn to print the material. And so here, all of these have to do with potentially making a material, and then rather than just machining, uh, learning how you test and characterize the material. The next group is if you have a biolab, there's this great recursion of Fab Labs making biolabs. So there's a somewhat like the Fab Lab network, there's a whole network of do-it-yourself biologists. iGEM is a really large collaborative competition in programming synthetic biology systems. How to make almost anything has spun off how to grow almost anything, which in turn inspired Bio Academy. That is a sister class you can take in the future. It covers all of these skills, but in particular, many of these skills use tools similar to Fab Labs, but instead of manipulating bulk materials, you're manipulating bioreagents. And so something in this space you could do this week if you have access to it. Then come textiles. So this is a nice recitation on everything to do with fibers: weaving, knitting, crocheting, felting, braiding, sewing, embroidering, all the different processes you can use to make things out of fibers. This is a nice page on how knitting machines work, how you program them. And there are these have come way down in cost of you can get programming attachments for these roughly $1,000 knitting machines. And so this is a page on design for it. Then let's see, this was an early student thesis in my lab on producing electronic circuitries by embroidering them. And the embroidery machines, uh, um, the let's see, I'm not sure what the successor to this one is, but these machines, uh, uh, there are dedicated embroidery machines and dedicated sewing machines, but then there are these hybrid machines. So yeah, here's another one, but about $1,000. And what they let you do is conventional sewing, but you can do programmable embroidery like this. And then the software for those is generally irritating and proprietary, but fortunately, it's now been open source. So there's PE Embroider, and then Ink Stitch is a nice extension to Inkscape. And so you can embroider functional things, and you can just embroider decorative things. And if you've never tried this before, whenever anybody embroiders anything in a lab, it's a magnet, and lots of people get excited, and it becomes one of the most popular tools. Um, so let's see, Stephen, what is turtle stitch? Ah, oh, this is a like a programming environment for embroidery. Oh, I get it. Turtle stitch. Interesting. Okay, I'll add that link. And if you get excited by all of that, then Fab Academy is another sister class, um, all about the skills for textile technology. Okay, that's the first half of class, and that's a non-exclusive list. This is to give you a feeling. Uh, if you haven't done three-axis machining, I would urge that. That's a core skill we used to have everybody to do. But all of these are good options, whatever excites you. And then, uh, let's see, Yuichi, what are you linking? Okay, this was embroidery in Wildcard Week. Oh, okay, using this coded environment for it. Nice, good. Okay, now the second half of class is we used to have everybody do composites. Uh, I would say the vinyl cutter is the most neglected tool, and composites is the most neglected process. Yeah, Richard was asking, and yeah, Richard, I'm going to add that Form Labs has a nice page on electroplating. So starting with a 3D print and then electroplating a metal part. And absolutely, electroplating would count for um, starting with a commodity printer and getting nice metal finishes rather than a $100,000 metal printer. And so that would be fine for this week. Um, yeah, Patrick, dead bug, I wouldn't count because that we basically covered that. Well, it doesn't count for two reasons. I introduced dead bug in electronics week, and then for this week's assignment, remember, there has to be a digital workflow that you can document and transfer. Dead bug is arts and crafts. It's manual skill training, so that wouldn't count. Yeah, UV printing. In fact, here I'll add that. There's a new Kickstarter for a UV printer. And UV printing is sort of in between inkjet printing and 3D printing. It jets ink that's then optically cured. And unlike other printing, one difference is you can print on absolutely anything. And another is you can get topography, not just flat surfaces. And so it's really beautiful. It pops. If you have access to a UV printer, UV printing on something else is fine. And I'll add UV printing. Okay, so now for the second half, I'm going to intro composites, which I vote as the least appreciated tool. So here's Sam's kayak. Here are paddles. Kenny made a bicycle. This is a hard shell briefcase. This is a small canoe. All of these are made in Fab Labs using the tools you have access to, but they're large, light, strong structures. So what's going on? The idea of composites is my shirt is floppy in compression, but in tension, it's very strong. I can't rip it just simply by pulling on it. Epoxy is really good in compression. You can't compress it further, but epoxy is terrible in tension. It'll tear or deform. So you have one material that's good in compression, one that's good in tension, and so you marry them, you combine them. So you put the fiber in the matrix. So state of the art is epoxy and carbon fiber, and that's used to make jumbo jets. Buildings around you, concrete is good in compression, but it tears, it cracks in tension. And so you put rebar, metal bars that handle the tension. Fiberglass, like in boats, are a composite. The circuit boards we use are a composite. Automobile tires are a belt and rubber. Old Adobe construction is clay with fiber, paper mache. And the most important composite of all is wood. Wood is wood fibers in a resin matrix. So the idea of composites is exactly that. It's putting fibers for tension in a resin matrix. So for the fiber, you can use chopped fibers. They're easy to work with, but they're not very good because you don't transfer forces between them. You can use filaments that you wind. You can use tapes that you lay up. And then the most common Fab Lab process is fabric. You take sheets of fabric and you lay them up. You can do it with glass. You can do it with carbon. We stay away from that in Fab Labs. I'm going to talk to safety at the end, and there's serious safety issues with glass and carbon. But there's great use of natural fibers. So cotton, silk, bamboo, wood, linen, burlap, all of those, they're not hazardous. They're environmentally friendly. They're easy to work with, but you can make surprisingly large, light, strong composites using natural fabrics. Then for the matrix, epoxy is common. Phenolic is used, for example, in the FR1 circuit boards. Cement is used in buildings. And then there's a fair amount of work on natural resins. So using plant resins to make more environmentally friendly resins. And then finally, in addition to fabric and resin, next door to that is laminates. So a killer project for this week is make a custom skateboard. And a common way to do this is not to start from the fabric, but you start with plies of wood, and you compress them in a mold and glue them all together to make a laminated structure. So to buy all of this, one of the good suppliers is boats. Um, so boat builders make lots of composites. So these are marine supply that are good sources. Then these are vendors specifically for composites. So fiberglass supply isn't just uh, um, isn't just fiberglass. Let's see, Benedict is asking that what are soluble resins for SLA are generally not plant-based. Generally, they're not environmentally friendly. I'll show you an alternative. This is another dedicated composite supplier. And then a really nice vendor, this one makes really beautiful plies of laminates, Lingrove. And then this is one I strongly recommend, Entropy Resins. The distinction is the ordinary epoxy you use is fairly unfriendly material. So you don't use it in a closed space. You need really good ventilation for the epoxy. Entropy Resins isn't open source, it's proprietary, but it's not 100% bio-based, but it's significantly bio-based, and it's much lower volatility. Let's see, I'll explain itching for fun when I get to the safety, which isn't just a joke. So Entropy Resins makes a epoxy you can use for the layup process. Like you see here, again, that's lower volatility, more environmentally friendly. Lysander, I'm going to talk again about protection very shortly. Um, so these are some of the vendors for composites. Now, there aren't really good design tools for composites uh, outside of state-of-the-art industrial production, but there's some guiding principles. So the most important principle is this one. When you take a composite beam that's light, flexible, you can't bend it. And the reason why is these are plies of the fabric in the beam. They're all in the resin matrix. And what's going on here is there's a radius of curvature. When you bend the beam, the outside has to travel further than the inside. And so what that means is you're pulling in tension on the fibers at the outside. And then if you bend the other way, you're pulling on the fibers on this side. So in fact, the ones in the middle don't do very much, and I'll mention that in a minute. That's why a single sheet of fabric is not a composite. You have to laminate multiple plies to have thickness, and it's the radius of curvature is what gives you the bending stiffness. And so, in fact, it's typical to put in a core. So since the core of the material isn't adding anything to it, honeycomb is used. You can put in cardboard forms. Let's see, the uh, uh, there's a beautiful series of cardboard skateboards where what you do is you laser cut a cardboard frame, you lay up a composite skin. It is the core, and it just stays in it. You make these beautiful skateboards. So typically you don't lay up dense layers of the composite. You lay up bottom layers, a core, and top layers to design it. And so to produce it, what you're going to do is, let's see, think I have linked here the key steps. Well, actually, let's see. Let me first sketch. So what we're going to do is we're going to make a mold. The mold, let's see. Let's say you want to make an auto body panel. You'll make a mold with the shape of the auto body panel. You're going to lay up the fabric. You're going to fill it with the resin, and then you're going to compress it. And the compression is the heart of it, which is there's a ratio of how much resin to how much fiber. As a beginner, you might have 50-50 fiber resin. State-of-the-art composites are maybe 90% fiber and 10% resin. So what you need to do is you need to infuse it with the resin, but you then need to get rid of all of the excess resin. Now, the first step is this. Oh, let's see. I'll fix that link. Fix exact flat. There's a notion of Gaussian curvature. If you take a fabric and you put it in an arbitrary mold, it'll have creases. It won't lay flat. So one of the things you need to do is you need to design in darts so that you have cuts in the fabric. So when you lay it in the mold, it lays in smoothly. And then you need to compress it. And so this is a link to many different pages of testing different types of materials under different compression. These are side views where you can see different kinds of compression and getting the fibers closer and closer together. So a simple way to compress it is to put a trash bag of water on it and just use the weight. Better is to use a vacuum, which I'll talk about in a minute. Better still is to mechanically clamp it and use a mechanically clamping force. A coupon is what you call a test part. And again, in these pages, we made many different kinds of coupons. And if you're going to start playing with composites, before you make a big composite part, you should just make these little coupons for testing your process. An open mold is you make a mold on one side, and then increasingly what's done are closed molds where you have a mating mold and then you bring the two mold parts together. And the difference between that is, well, actually, sorry, before I get to that, let me get to how does the resin get in? Pre-preg is where it's already infused in the fabric, and typically you need to refrigerate it. RTM and VA RTM is resin transfer, where you force it under pressure. What we do is wet layup. And so Sam, who keeps coming up this week, there's a nice, oh, no. Yeah, so when I complain about videos, he has a nice YouTube video. I'll see if I can find it. Yeah, the links out of our repos break. And unfortunately, that video shows all the steps, but it shows the wet layup. And so wet layup is you put in a layer of fabric, you spread the epoxy, you spread it out, then another layer. And so it's just literally that, it's wet layup. Then you need to compress it. So compression molding is where you make a press and you close clamps. And that works up to reasonable sizes. For bigger sizes, you then vacuum bag. And so this is an app note on vacuum bagging. And that's another broken link that I'll fix. I'll fix that link, which was an app note, but Adrian's helpfully put this one in. So in vacuum bagging, typically it's a one-sided mold. There you then lay up your composite. Then there's a bleeder and a breather. The bleeder is a film that has little holes to let the resin come out. And then the breather is like uh, cotton, think of it as batting. It's a porous material. Then you pull a vacuum, and then you have the whole weight of air pressure on top of you. And the air pressure squeezes the excess resin out through the bleeder into the breather film. And so what's good about vacuum bagging is it works over any size area. You don't, the force you need doesn't vary because you're not producing the force, you're just generating the vacuum. What's bad about vacuum bagging is it's a fair amount of work to make the vacuum bag and do all of those steps. And so generally what I prefer is, let me just explain that same image again. So you make one side of the mold, lay up your fabric, spread some resin, lay up another ply of fabric, spread some resin, lay up however many plies. You bring in the other side of the mold, then we're going to clamp the whole thing. And so the clamping force depends on the size of the mold, and your ability to clamp goes down as it gets bigger. So you couldn't make an airplane wing this way. But increasingly, this is done with large molds and industrial parts. And on Fab Lab scale, it's fine. Then when you clamp it down, you can get even more compression than air pressure. And then what you do is, and you need to be prepared for this, you're going to squirt the excess resin out the side. So you need to design the workplace so that you seal the mold, and then you have a room here where the excess resin just comes out and goes down the side, and you squeeze it out to do a two-sided mold compression. So that's the basic process. And then a final thing you need to know is if you look at like a carbon fiber bicycle. Let's see. Stephen, did you find my broken link? Okay, great. This is great. This is this is a app note that shows all of the steps that I just went through and talks about each of the steps for vacuum bagging. But again, I recommend learning how to do closed tool molding. So when you look at a carbon fiber bicycle and you see this beautiful shiny finish, once you're finished the composite process, it doesn't look like that coming out of the mold. And so the final step is a clear coat that typically there's a somewhat rougher surface, and then the clear coat goes over all of that to give you that smooth, shiny finish. So to make the mold, there are many ways to do it. You can machine the mold, and so Kenny, who made the bicycle, in this case, he's machining a mold and casting this beautiful part in it. I had talked about, this was Kenny folding a mold. And again, if we, let's see, composite cardboard surfboard. So in the composite cardboard surfboards, it's a variant of folding the mold where you make a mesh in exactly the shape you want. You lay up the composite around it, and then you don't need to remove the cardboard. It stays in the middle of your surfboard. And in fact, I mean, you can make it opaque, but people admire these just because they're really beautiful looking. Um, that's machining a mold, folding a mold, and oh, sorry, I have it right here. That uh, this last link was to uh, skinning it. So, and if you go back to here in the bicycle, this is another example where, again, this was Kenny who I mentioned, where he makes this cardboard form. Here he's vacuum bagging in this case. And then the cardboard just stays in the bike frame. Once you're done, all the load is done by the fiber and resin outside, and the cardboard just stays in as the core. Now, safety. Here's the issue. Carbon fiber and glass fiber is exactly the danger of asbestos. So, asbestos led to serious lung disease. Short fibers of glass or carbon, if you breathe them, they get in your lungs, and over time, you can get lung disease. And the joke that's not a joke about itching is if they get in your skin, that they're really irritating, and there's no easy way to get them back out. So carbon fiber and glass fiber are perfectly harmless if you just cut them with scissors, and they're harmless if you lay them up. The issue is if you do anything after that. So if you drill them, or you can cut them easily with scissors, but once the resin is hardened, you can't cut them. You need to machine it or drill it or sand it. Any of those operations create short fibers that are very, very hazardous. So uh, let's see, carbon fiber composite PPE. When you're working on carbon fiber, you really need to look like an astronaut. And if you try to shortcut that, the end result is serious hazards. So you don't want to be breathing it. You don't want it in your eyes. You don't want it anywhere in your skin. And there's a lot of use of, in particular, some with carbon fiber, much more with fiberglass, that's just not safe. So if you want to use those materials, you need the full PPE. But again, if you're using the low volatility resin and, for example, natural fabric, then the protection you need is similar to molding and casting week, which is this is sticky, gooey stuff. It's hard to get off. So you need protection for that. You don't want it to splash in your eyes, but it's no worse than that. Um, the second issue is if you're not using low volatility epoxy, it generates a lot of fumes, so you need really good ventilation. And then the final thing is the exotherm. Just like molding and casting, this can produce a tremendous amount of heat depending on the size of the part, the size of your section. And you need to be prepared to cool it for the exotherm. So the summary from all of that is, unless you're really well equipped, just stay away from glass and carbon fiber. You have to really be pushing performance to even see the difference between natural fiber composites and glass or carbon fiber. And so, in the boat project, Sam made composite paddles, and then he made the frame, laid the skin, and here in effect the core of the composite is the wooden frame, and he's laying up the composite skin directly on the frame to make this composite kayak. So this week is right at the Venn diagram intersection of make something big and molding and casting. And if you combine those with fabric and infusion and compaction, then suddenly you can make, instead of, so in make something big, I challenge you to make something that wasn't flat. Right off the bat, in composites, you can automatically make large, light, curved, smooth surfaces. And so it really extends the capability of a lab. And it builds on all the skills we've covered, but now to make composites. So that's why I suggest this is probably the least appreciated technique. It really significantly expands the space of what you can make with composites in your lab. Okay, so that's a half a class tour on lots of different options for Wildcard and a half a class tour on composite layup. Any of those are fine for this week. See, just catching up with the chat. And let me come back to what you do has to involve a computer in design and manufacturing. It has to be something we haven't covered. And then very importantly, for this week, we don't tell you the assignment, you have to tell us the assignment. And you could choose to make this completely unrelated to your final project, but let me get back to this note. Schedule. See, Jacob is asking, Jacob, the compression is the same for any of these. When you skin, you can either vacuum bag or do compression molding. So in Wildcard week in composites, so here this shows Kenny made the cardboard frame, and here Kenny is, this is now the vacuum bag evacuated, curing the composite around the cardboard frame. And so you can either make a form that matches the inner form, or you can vacuum bag around it. So Jacob, the size limit of this process is so the Boeing 787 barrel winding. This is taking a tape and winding it over and over around a barrel, making the whole tube, the whole body of
Oh,
the
the time
jumbo
is
jet.
different.
Somebody needs to mute. This is doing, and I got to visit this factory. There's a mandrel, and then there's a tape. I don't know if it shows all the steps. And then you wind the tape around that whole barrel, and you make the body of a jumbo jet. So you can use this to make a jumbo jet if you want this week. So let me go back to, as of today, you can sign up for final presentations if you're far enough along. And in the review today, I'd say it was about 50-50 for who was ready and who wasn't. To be ready for the final presentation, you should have CAD for the final project. You should have a system diagram of the elements. You should have a schedule for finishing. And so if we go back to the calendar, this week you're going to be doing Wildcard. You could veer off and do something completely new. Best is to tie this to the final project. So Jacob, for the 787, it's pre-preg tape. So the tape is already infused with the resin. They then wind it around the barrel. And then it goes into an autoclave where the overpressure comes from pressuring the giant autoclave. So you're going to work from this week to this week. Next week, there's no new topic. I'm just going to give you a tour of final projects and fab examples. There's the week after that. Then the week after that, I'll talk about managing invention and intellectual property. You have another week to work, and then you're presenting. And along the way to that, we need the weekly assignments done. And once again, you can use the final project to check off the weekly assignments, but you need to show us where it is. So as I stressed in the review, right now we're deep into triage time. I want to see in the final project that you can make a finished project using all the skills. But like, to take the submarine example, if the submarine submerges and come up again, that's enough at this point. You don't yet have to have the full navigation system for the submarine working. That can come later. Okay, with that note, my caution was this is one of the most fun weeks, opening up this universe of challenges. The difficulty in this week will just be managing your attention to stay focused. No recitation this week. The week after, we'll have a startup recitation. As usual, the global open time, and please rely on it. A lot of people who come up in the random review struggling with issues come to the global open time and get help in it. Okay. Yeah, global team open time is noticing attendance has been going down, not up. You should all be leaning on, you've got this hot and cold running gurus at your disposal to help you. Take advantage of it. And in particular, you don't need to come with good questions. You can come with help. I'm overwhelmed and nothing's working and I'm confused. And so come with problems, not solutions, and they'll help you. Okay. Happy Wildcard. I look forward to seeing what you do. And each year, some new ideas come in that trickle throughout the whole Fab network. So I'll see you in a week. Bye-bye from London.
Adios.
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 Bye.
Cheers.
Oh,
Bye-bye.
David.
Cheers.
Good.